Hello everyone and welcome back to Mitchell's Physics Review. Today we will be working on RC circuits. Let's take a look at our problem. The pair of capacitors in the figure below are fully charged by a 22-volt battery. The battery is disconnected and the switch is then closed. Let's take a look at our first circuit diagram. We have two capacitors and one resistor in parallel. So to start, let's start thinking about some of our rules of capacitors in parallel. Next, we have some givens. We're given that the change in V of the initial battery is, or that the circuit is charged to by the battery, is 22 volts. The resistance is 500 ohms. The capacitance on one of the capacitors is 3 microfarads, and the capacitance on the other capacitor is 2 microfarads. Now that we've taken a look at this circuit, let's take a look at part A. After 3.4 milliseconds has elapsed, how much charge remains on the 3 microfarad capacitor? To start, we know that the capacitor is discharging. From our RC equations, we can use the equation of charge is equal to the total charge times E raised to the negative t over the time constant tau. But as you can see in our givens, we're not really given any of these, so we're going to have to work our way through and find a couple unknowns. To do this, let's start before the switch is closed and by combining the circuit. From earlier, our rules of capacitors in parallel is that the total or equivalent capacitance is equal to the capacitance of one plus the capacitance of the other. So we can simply say the 2 microfarads plus 3 microfarads equals 5 microfarads. Now we can draw a new circuit where we only have one resistor and one capacitor in series in this switch open. We can also find the total charge before the switch is closed, which will just be the total charge is equal to the equivalent capacitance times the voltage, so 5 microfarads times 22 volts equals 110 microcoulombs. Now, let's take a look at after the switch is closed. After the switch is closed, we can now look at our time constant, which is tau is equal to R times C. We just found our equivalent capacitance of 5 microfarads, or 5 times 10 to the negative 6 farads, and we're given the resistance of 500 ohms. Once we plug into the calculator, we can get that the time constant equals to 2.5 times 10 to the negative third seconds. Now, we finally found enough so that we can start plugging in and find the charge on the capacitors while discharging. We can start by using the 110 microcoulombs as our total charge. E is going to stay the same. We can use the given time of 3.4 times 10 to the negative third seconds, which we converted from 3.4 milliseconds, over tau, which we just calculated to be 2.5 times 10 to the negative third. From there, we get that charge is equal to 28.23 microcoulombs after this circuit has been discharging for 3.4 milliseconds. However, we must remember that this is total charge. Now, this is where we're going to bring in some more rules of capacitors in parallel. Our total charge should be equal to the charge on the 3 microfarad capacitor plus the charge on the 2 microfarad capacitor. But, as you can see, we have two unknowns, so we're going to need to substitute in. In parallel, though, we know that the voltage on both of the capacitors should be the same. So we can start by setting them equal to each other, substituting in for charge over capacitance, which is Q3 over 3 microfarads equals Q2 over 2 microfarads, and solving Q2 in terms of Q3, which is 2/3 Q3 equals Q2. We can plug this into our previous equation and then do the algebra to solve to get Q3 is equal to 16.9 microcoulombs. Now let's take a look at part B. After 3.4 milliseconds has elapsed, how much charge remains on the 2 microfarad capacitor? Well, we just solved for Q3 and the total charge earlier. So if we use the same equation of Qt equals the charge on the 3 microfarad capacitor plus the charge on the 2 microfarad capacitor, we can plug in the two values we solved for, do the algebra, and get that the charge on the 2 microfarad capacitor is equal to 11.3 microcoulombs. Now, let's look at part C. What is the current in the resistor at this time? For part C, we're going to need to start by finding a voltage because the battery is now removed and the capacitors are discharging. However, once again, since the three devices are in parallel, we know they will all share the same voltage. Since we already know the charge and capacitance, we can use either the 3 microfarad capacitor or the 2 microfarad capacitor to find the voltage. In this case, I chose the 2 microfarad capacitor. So change in V is equal to the charge 2 over C2, which is 11.3, which we just solved for, over 2, which was given, to find the change in V equals 5.65 volts. Then we can go to the equation I equals to change in V over R, where we plug in the V we just found, the given R, and we get that I is equal to 0.0113 amps or 11.3 milliamps. Overall, for this problem, I really struggled with part A. We had a lot of unknowns and I was getting stuck on where we were going to find them. So what helped me was to take a look at the circuit before the switch was closed and to simplify it by making it only 2 devices instead of the 3. I hope this video helped you learn a lot, as it did me, and always remember, if we're dealing with circuits, don't forget about your parallel and series equations. Have a great day.